In a world full of questions where wisdom knows no boundaries, join us on a journey of enlightenment and endless learning. Eternal Education Network. Discover the eternal. NASA's groundbreaking discoveries on mysterious Mercury. Unveiling the mysteries of the solar system's smallest planet. Dive deep into the astonishing discoveries NASA has made on Mercury, the smallest and most mysterious planet in our solar system. From its giant iron core and unique magnetic field to the unexpected discovery of water ice in its polar craters, Mercury defies everything we thought we knew about planets close to the Sun. In this detailed video, explore the latest findings from NASA's Messenger and Mariner 10 missions, as well as insights from the upcoming BepiColombo mission. Discover how Mercury's unusual features, like its extreme temperature fluctuations, volatile elements, and cratered surface, are helping scientists understand the formation of planets, both in our solar system and beyond. Learn about the Caloris Basin, Mercury's volcanic history, tectonic activity, and the intriguing theories surrounding its enormous core. Find out why studying this planet is critical for understanding exoplanets and the evolution of the inner solar system. Stay tuned for insights into how these missions are rewriting what we know about the smallest planet and what future space missions like BepiColombo aim to uncover. Key topics covered: NASA's Mariner 10 and Messenger missions, BepiColombo mission goals, Mercury's extreme temperatures and water ice, the planet's magnetic field and large iron core, geological features like the Caloris Basin and lobate scarps, Mercury's formation and evolution, comparison with exoplanets and planetary systems. Make sure to like, subscribe, and hit the bell icon to stay updated with the latest space discoveries. Mercury, the innermost planet of our solar system, has long intrigued astronomers and scientists due to its enigmatic characteristics. As the smallest and closest planet to the Sun, Mercury presents unique challenges for exploration, making it an object of curiosity for space agencies worldwide, especially NASA. Over the decades, NASA's missions to Mercury have unveiled a multitude of mysteries about the planet, deepening our understanding of the solar system's formation and evolution. This detailed analysis explores the findings NASA has made regarding Mercury, from its physical characteristics and extreme environment to its magnetic field and geological history. We will also discuss the broader implications of these findings and how they continue to shape planetary science. Early observations and challenges in studying Mercury. Mercury has been known to ancient civilizations for thousands of years, but its proximity to the Sun made it difficult to observe. Early astronomers, relying on Earth-based telescopes, found it challenging to study the planet because it is often lost in the Sun's glare. Mercury's orbit, which is more elliptical than any other planet in the solar system, also made predicting its position complex. It wasn't until the advent of space exploration that scientists began to unravel Mercury's mysteries in earnest. Before NASA's missions, Mercury was largely a mystery, known only to have a heavily cratered surface and an extreme environment due to its proximity to the Sun. NASA's exploration of Mercury Mariner 10 and Messenger, NASA's first close-up investigation of Mercury, began with Mariner 10, which flew by the planet 3 times between 1974 and 1975. This mission provided the first detailed images of Mercury's surface and revealed a planet that was similar in some ways to the Moon, with large impact craters and smooth plains. However, Mariner 10 only imaged about 45% of Mercury's surface, leaving much of the planet unexplored. In 2011, NASA's Messenger, Mercury Surface, Space Environment, Geochemistry and Ranging spacecraft, became the first to orbit Mercury, providing a treasure trove of data that has revolutionized our understanding of the planet. Messenger's mission lasted until 2015 and brought unprecedented insights into Mercury's geology, magnetic field, composition and environment, key mysteries and discoveries about Mercury. Mercury's extreme temperatures and thin atmosphere. Mercury is often considered a planet of extremes due to its position so close to the Sun. One of NASA's key discoveries relates to the planet's extreme temperature fluctuations. During the day, Mercury's surface temperature can soar to about 430 degrees Celsius, 800 degrees Fahrenheit, while at night, temperatures plummet to as low as -180 degrees Celsius, -290 degrees Fahrenheit. These extremes are caused by the planet's lack of a significant atmosphere to retain heat. Mercury does have an exosphere, a very thin atmosphere composed mostly of oxygen, sodium, hydrogen, helium, and potassium. NASA found that this exosphere is not stable and is continuously being replenished by interactions with the solar wind and micrometeoroid impacts. The solar wind strips away atoms from Mercury's surface, which then enter the exosphere. The presence of water ice in Mercury's polar craters. One of the most surprising discoveries made by NASA's Messenger mission was the detection of water ice in Mercury's permanently shadowed polar craters. Despite Mercury's extreme daytime heat, some craters near the poles never receive sunlight, allowing ice to remain frozen in these regions. Messenger's neutron spectrometer detected elevated hydrogen concentrations, indicating the presence of water ice beneath the surface. These ice deposits are likely remnants of comets or meteoroids that collided with Mercury in the past. Scientists believe that Mercury's water ice could be billions of years old, providing clues about the history of water in the inner solar system. Mercury's unexpected magnetic field. One of the major surprises of the Mariner 10 and Messenger missions was the discovery that Mercury has a magnetic field, albeit one that is much weaker than Earth's. This was unexpected because Mercury is so small that it was thought its core would have solidified long ago, preventing the generation of a magnetic field. Messenger's data revealed that Mercury's magnetic field is generated by a dynamo effect in its partially molten core. What makes Mercury's magnetic field even more peculiar is that it is not symmetric. It is offset from the planet's center by about 20% of Mercury's radius, meaning that the magnetic field is stronger in the northern hemisphere than in the southern hemisphere. This asymmetry has puzzled scientists as it contrasts with the more symmetric magnetic fields found on Earth and other planets. It suggests that the dynamo process in Mercury's core may be unique, or that the planet's interior structure is significantly different from what was previously thought. Mercury's large iron core. Another significant discovery about Mercury is its large metallic core, which makes up about 85% of the planet's radius, a much larger proportion than Earth's core. This unusual structure has raised questions about how Mercury formed and evolved. There are several hypotheses to explain Mercury's large core. One theory suggests that the planet may have formed with a more Earth-like composition, but lost much of its outer rocky material due to a giant impact or intense solar wind stripping during its early history. This would have left Mercury with a higher core-to-mantle ratio compared to other planets. Messenger's findings also showed that Mercury's core is still partially liquid, contributing to the generation of the planet's magnetic field. Additionally, the spacecraft detected that Mercury's core has a solid inner layer, similar to Earth's inner core, surrounded by a liquid outer layer. Surface geology, tectonics, volcanism and craters. Mercury's surface is dominated by impact craters, much like the Moon's. However, Messenger revealed that the planet also has extensive smooth plains that were likely formed by volcanic activity early in its history. These plains are evidence that Mercury was once geologically active, with lava flows filling in large impact basins. One of the most prominent features on Mercury's surface is the Caloris Basin, a massive impact crater that is about 1,550 kilometers or 960 miles in diameter. This basin was created by a giant asteroid impact early in Mercury's history and is surrounded by mountain ranges that were pushed up by the force of the collision. Messenger also discovered that Mercury has long, steep cliffs known as lobate scarps, which were formed by the planet's crust contracting as its interior cooled and solidified. These cliffs indicate that Mercury has undergone significant tectonic activity, with parts of the surface being thrust upward as the planet's diameter shrank by as much as 7 kilometers or 4.3 miles. Volatile elements and planetary composition. One of the surprising findings of the MESSENGER mission was the presence of volatile elements like sulfur, potassium, and sodium on Mercury's surface. These elements were not expected to be abundant on a planet so close to the Sun, where intense heat would have driven them off during Mercury's formation. The presence of these volatiles has led scientists to reconsider their models of how Mercury formed. One possibility is that Mercury formed in a cooler region of the solar system and migrated inward, or that it accreted material from cooler, volatile-rich regions after it formed. The discovery of these elements also has implications for Mercury's volcanic history. The presence of sulfur suggests that Mercury's early volcanic eruptions were likely more explosive than previously thought, as sulfur can lower the melting point of rock, allowing magma to erupt more easily. Mercury's role in understanding planetary formation. Mercury's unique characteristics provide critical insights into the processes that shaped the inner planets of our solar system. Its large core, magnetic field, and volatile elements challenge existing models of planetary formation and highlight the diversity of planetary bodies in the solar system. Understanding Mercury's geological history and interior structure also helps scientists learn more about exoplanets in other solar systems. Many exoplanets discovered in recent years orbit very close to their parent stars, similar to Mercury's orbit around the Sun. By studying Mercury, scientists can gain insights into how these hot exoplanets may have formed and evolved. Despite the wealth of data provided by Mariner 10 and MESSENGER, many questions about Mercury remain unanswered. Some of the key mysteries that future missions hope to solve include the origin of Mercury's large core. Why does Mercury have such a disproportionately large core compared to other terrestrial planets? The asymmetry of Mercury's magnetic field. What causes the offset in Mercury's magnetic field, and how does this relate to the planet's interior structure? The age and source of Mercury's polar ice. How old are the water ice deposits in Mercury's polar regions, and where did the ice come from? And finally, Mercury's geologic activity. Is Mercury still tectonically active today, and what processes are driving this activity? The next major mission to Mercury is a joint project between the European Space Agency, or ESA, and the Japan Aerospace Exploration Agency, known as JAXA. This mission is called BepiColombo. Launched in 2018, BepiColombo is expected to arrive at Mercury in 2025. The mission consists of 2 spacecraft, the Mercury Planetary Orbiter, or MPO, and the Mercury Magnetospheric Orbiter, or MMO, each designed to study different aspects of the planet. BepiColombo aims to build on the discoveries made by Mariner 10 and MESSENGER, providing even more detailed observations of Mercury's surface, interior, magnetic field, and exosphere. Here's a detailed breakdown of what the mission hopes to achieve and its broader scientific goals. The Mercury Planetary Orbiter, or MPO, is the primary spacecraft in the BepiColombo mission, tasked with studying Mercury's surface and interior structure. Its suite of instruments is designed to capture high-resolution images of the planet's terrain and analyze its surface composition, providing critical data on Mercury's geology and mineralogy. Key instruments on the MPO include the stereo camera and imaging systems, which will capture detailed images of Mercury's surface. This allows scientists to map its topography, study craters, ridges, and other features, and investigate the planet's tectonic and volcanic history. The Mercury Radiometer and Thermal Imaging System, or MERTIS, will provide data on Mercury's surface composition by measuring the heat emitted by different minerals. This will help scientists determine the types of rocks present on Mercury and how they formed. The BepiColombo laser altimeter, known as BELA, will precisely measure the planet's surface topography. This helps scientists construct detailed maps of Mercury's surface and study features like craters, scarps, and plains in unprecedented detail, aiding in understanding the tectonic forces that shape the planet's surface. The Gamma Ray and Neutron Spectrometer, or MGNS, will detect gamma rays and neutrons emitted from Mercury's surface. This helps scientists determine the elemental composition of the planet, especially in areas where water ice has been detected. The Mercury Imaging X-ray Spectrometer, or MIXS, will measure X-rays emitted from the planet's surface to determine the composition of the rocks. This is particularly important for understanding the distribution of elements like iron, silicon, and sulfur, which play a role in Mercury's volcanic and tectonic activity. The Mercury Magnetospheric Orbiter, or MMO, also known as MEO, is designed to study Mercury's magnetic environment and how it interacts with the solar wind. Since Mercury has a magnetic field similar to Earth's but much weaker and offset, understanding its magnetosphere is crucial for revealing how the planet's interior works and how it has evolved over time. Key instruments on the MMO include the magnetometer, or MAG, which will measure Mercury's magnetic field in detail. This allows scientists to study its strength, structure, and origin, crucial for understanding the dynamo processes in Mercury's core that generate the magnetic field. The Plasma Wave Investigation, or PWI, will study electromagnetic waves in Mercury's magnetosphere. This helps scientists understand the interaction between the planet's magnetic field and the solar wind, creating phenomena like magnetospheric storms, which provide insights into Mercury's magnetic and atmospheric environment. The Energetic Particle Detector, or EPD, will study energetic particles in Mercury's magnetosphere and how they interact with the planet's surface and exosphere. Understanding these interactions is key to revealing how Mercury's thin atmosphere is constantly being loaded by the solar wind. The Sodium Atmospheric Spectral Imager, or MESASA, will investigate Mercury's thin atmosphere or exosphere by observing the spectrum of solar. This helps scientists understand how solar radiation and micrometeoroid impacts contribute to the formation and maintenance of the exosphere. With its array of advanced instruments, BepiColombo is expected to provide answers to many of the unresolved mysteries of Mercury. The following are the key areas of scientific inquiry that BepiColombo will address. One of the most significant goals of the BepiColombo mission is to gain a better understanding of Mercury's internal structure, particularly its core. Scientists hope to refine estimates of the size and state of Mercury's core, whether it is entirely liquid or has a solid inner core like Earth's. By combining data from the MPO's gravimetric instruments and the spacecraft's precise tracking system, scientists will be able to measure Mercury's gravitational field with high accuracy. These measurements can reveal subtle variations in the planet's mass distribution, which will in turn help scientists model its internal structure. Understanding Mercury's core is essential for solving the mystery of how it generates its magnetic field and what makes it so different from the cores of other terrestrial planets. BepiColombo's study of Mercury's magnetic field will build on the findings of MESSENGER by providing higher resolution data. One of the primary goals is to better understand the asymmetry of the magnetic field and how it is generated within the planet's core. BepiColombo will also investigate how the planet's magnetic field interacts with the solar wind. Mercury's close proximity to the Sun subjects it to intense solar radiation and powerful streams of charged particles. These interactions create a dynamic magnetosphere that differs significantly from Earth's. Understanding how Mercury's magnetosphere works will also provide insights into how magnetic fields operate on other planets, especially those in close proximity to their parent stars. The surface of Mercury is rich in geological features that provide clues to the planet's history. BepiColombo will be able to study volcanic plains, tectonic scarps, impact basins and craters in far greater detail than previous missions. By mapping the surface at higher resolution and studying the composition of rocks and minerals, BepiColombo will help scientists reconstruct the planet's geological history. One key question that BepiColombo aims to answer is whether Mercury experienced long periods of volcanic activity or whether its surface cooled and became inactive early in its history. The mission will also investigate the planet's tectonic activity, particularly the formation of lobate scarps and other features that suggest the planet is contracting as its core cools. BepiColombo will further investigate the water ice deposits in Mercury's permanently shadowed craters at the poles. By combining data from its spectrometers and thermal imaging systems, the mission will provide more detailed information about the composition, depth, and distribution of the ice deposits. Scientists are particularly interested in determining the age of the ice and whether it was delivered by comets, meteoroids, or other sources. The presence of water ice on a planet as close to the Sun as Mercury is a paradox that challenges our understanding of the solar system's thermal dynamics. BepiColombo will provide critical data to help solve this mystery, potentially revealing whether similar processes could occur on other airless bodies in the solar system or beyond. BepiColombo's instruments will conduct a detailed survey of Mercury's surface chemistry, focusing on volatile elements such as sulfur, potassium, and sodium. The presence of these elements, which were unexpected given Mercury's proximity to the Sun, has led scientists to reconsider their models of planetary formation. By analyzing the distribution of volatile elements and mapping their concentrations across the planet's surface, BepiColombo will help scientists understand how these elements were retained during Mercury's formation and how they have influenced the planet's geological and volcanic processes. This could provide insights into the early conditions of the solar system and how the inner planets evolved. One of the broader scientific goals of studying Mercury is to better understand planetary systems beyond our own. Mercury provides a unique case study in comparative planetology because it represents an extreme end of planetary formation, a small, dense planet located close to its parent star. By studying Mercury in detail, scientists can refine their models of planetary formation and evolution, which can then be applied to exoplanetary systems. Many of the exoplanets discovered in recent years are hot planets that orbit very close to their parent stars, similar to Mercury's position in the solar system. These planets are often subjected to intense radiation and solar wind, much like Mercury. Understanding how Mercury's magnetic field, atmosphere, and surface have evolved under these extreme conditions can provide valuable analogues for interpreting observations of exoplanets. Additionally, the discovery of water ice on Mercury raises the possibility that volatile-rich exoplanets or moons in similar star systems might also harbor ice deposits, even in unexpected places. Despite the progress made by NASA's Mariner 10, Messenger, and the upcoming BepiColombo mission, many mysteries about Mercury remain. Future missions may aim to answer the following questions. Is Mercury still geologically active? While Messenger and BepiColombo will provide data on Mercury's tectonic features, it remains uncertain whether the planet is still undergoing tectonic activity today. Future missions equipped with seismometers could potentially detect active quakes on Mercury, providing a clearer picture of the planet's current geological activity. How did Mercury's core form? The origin of Mercury's large core remains one of the most perplexing questions in planetary science. A mission focused on studying the deep interior of Mercury, perhaps using techniques similar to those used by NASA's InSight lander on Mars, could provide more definitive answers about how the planet's core formed and evolved. Could Mercury's ice be a source of resources for future missions? As space agencies around the world plan for human exploration of the Moon, Mars, and potentially other planets, Mercury's water ice deposits have raised intriguing possibilities for the future of space exploration. The presence of water in the form of ice could, in theory, support future robotic or human missions to the planet by providing a vital resource for drinking water, oxygen, or even fuel. While Mercury's extreme temperatures and proximity to the Sun make it an unlikely candidate for colonization, The discovery of ice offers new directions for research into the availability of resources on other celestial bodies, especially in harsh environments. Mercury's unique environment also makes it a fascinating case study for scientists planning missions to other airless bodies, such as the Moon or asteroids, where water ice might exist in permanently shadowed regions. Understanding how Mercury's ice deposits formed, survived and evolved over billions of years will be valuable in guiding future missions that may seek to harvest such resources. The mysteries of Mercury's formation and evolution. Mercury's formation, a unique history. Theories about how Mercury formed have evolved as new data from Mariner 10, Messenger and other missions have become available. Mercury's large core, thin mantle and unusual surface composition suggest that the planet may have undergone a different formation process compared to other terrestrial planets like Venus, Earth and Mars. One leading hypothesis is that Mercury may have started out with a composition more similar to Earth, with a thicker mantle and crust. However, at some point in its early history, it may have been struck by a large impactor, which stripped away much of its outer layers, leaving behind a dense, iron-rich core surrounded by a thinner mantle and crust. This impact theory is supported by Mercury's high density and its relatively small size compared to other planets in the inner solar system. Another hypothesis suggests that Mercury may have formed in a region of the solar system with an unusually high concentration of iron, which would explain its large core and metallic surface composition. However, this theory is harder to reconcile with the presence of volatile elements like sulfur and potassium, which would have been expected to evaporate in the intense heat of the early sun. BepiColombo's detailed study of Mercury's surface and interior composition will help to test these competing theories and provide new insights into the planet's origins. Mercury's geological evolution. Mercury's geological evolution has also been a subject of intense study. Early in its history, Mercury experienced widespread volcanic activity, which resurfaced large portions of the planet and filled in many of its craters. The discovery of smooth plains by Mariner 10 and Messenger provided evidence of this volcanic activity, which may have lasted for hundreds of millions of years. However, as Mercury cooled, its volcanic activity diminished and its surface began to contract. The formation of lobate scarps, long, steep cliffs that cut across the planet's surface, is a direct result of this contraction. These scarps indicate that Mercury's interior has continued to cool and shrink over billions of years, causing the surface to buckle and form these dramatic cliffs. Interestingly, some of these scarps appear to be relatively young, suggesting that Mercury's interior may still be cooling and contracting today. If this is the case, then Mercury could still be geologically active, with tectonic forces slowly reshaping its surface over time. BepiColombo's high-resolution imaging and altimetry will help scientists study these scarps in greater detail and determine whether they are still evolving. The mystery of Mercury's volatiles. One of the biggest mysteries revealed by Messenger was the presence of volatile elements on Mercury's surface, such as sulfur, potassium and sodium. These elements are easily vaporized by heat, and their presence on a planet so close to the Sun was unexpected. Their abundance suggests that Mercury's surface may have been less affected by the Sun's intense heat than previously thought, or that they were delivered by external sources like comets or meteoroids after the planet's formation. BepiColombo's instruments will study the distribution of these volatile elements across Mercury's surface, helping scientists understand how they got there and why they remain. This research will provide important clues about Mercury's early environment and its interactions with the Sun and other celestial bodies. The presence of volatiles also has implications for Mercury's volcanic history. Sulfur, in particular, plays a key role in lowering the melting point of rock, making it easier for magma to erupt onto the surface. The discovery of sulfur suggests that Mercury's volcanic eruptions may have been more explosive than previously thought, which could explain some of the smooth plains observed on the planet. Mercury's magnetic field, first detected by Mariner 10 and later studied in greater detail by Messenger, is one of the planet's most intriguing features. Unlike Venus, Mars and the Moon, which have little to no magnetic field, Mercury has a global magnetic field that is generated by a dynamo effect in its core. However, Mercury's magnetic field is much weaker than Earth's and is offset from the planet's center by about 20% of its radius. This asymmetry in the magnetic field is a mystery that scientists have yet to fully explain. One possibility is that the structure of Mercury's core is different from that of Earth, with a solid inner core and a partially molten outer core that generates the magnetic field. The offset magnetic field could be a result of differences in the way heat is transferred from the core to the mantle, or it could be related to the planet's unique internal dynamics. BepiColombo's magnetometers will map Mercury's magnetic field in even greater detail than Messenger, providing crucial data to help scientists understand how the field is generated and why it is so asymmetric. This research will also shed light on the cooling history of Mercury's core and how it differs from other terrestrial planets. Mercury's proximity to the Sun means that it is constantly bombarded by the solar wind, a stream of charged particles emitted by the Sun's outer layers. These particles interact with Mercury's magnetic field and exosphere, creating a dynamic environment that is unlike anything seen on Earth or other planets. Messenger provided the first detailed observations of how the solar wind interacts with Mercury's magnetic field, revealing that the planet's magnetosphere is much smaller and more dynamic than Earth's. The solar wind can compress Mercury's magnetosphere to within just a few hundred kilometers of the planet's surface, and magnetic reconnection events, where the magnetic field lines are stretched and then snapped back together, occur much more frequently than on Earth. These interactions can strip particles from Mercury's surface and send them into space, where they form a thin exosphere around the planet. Mercury's exosphere is made up of atoms like hydrogen, helium, sodium and potassium, which are constantly being replenished by the solar wind and micrometeoroid impacts. However, the exosphere is so thin that it is barely detectable, making it difficult to study. BepiColombo's plasma instruments will study Mercury's magnetosphere and exosphere in greater detail, helping scientists understand how the solar wind affects the planet's surface and atmosphere. This research will also provide insights into how other airless bodies in the solar system, such as the Moon and asteroids, interact with the solar wind. Mercury's exosphere is one of the most unique atmospheres in the solar system. Unlike the thick atmospheres of planets like Earth, Venus or Mars, Mercury's exosphere is extremely thin and composed of atoms that are constantly being stripped away by the solar wind or micrometeoroid impacts. These atoms form a tenuous cloud around the planet, which is replenished by particles that are kicked up from Mercury's surface. The primary components of Mercury's exosphere are hydrogen, helium, sodium and potassium, with trace amounts of other elements. The source of these elements is thought to be the planet's surface, which is constantly bombarded by solar radiation and micrometeoroid impacts. These impacts can release atoms from the surface and send them into space where they form the exosphere. The discovery of sodium in Mercury's exosphere was one of the key findings of the Mariner 10 mission, and Messenger confirmed that sodium is one of the most abundant elements in the exosphere. Sodium atoms are highly reactive and are easily affected by the sun's radiation, making them a valuable tracer for studying the dynamics of Mercury's exosphere. BepiColombo will study the composition and dynamics of Mercury's exosphere in greater detail, helping scientists understand how the solar wind and micrometeoroid impacts affect the planet's atmosphere. This research will also provide insights into how exospheres form and evolve on other airless bodies in the solar system. The discoveries made by Mariner 10 Messenger and the upcoming BepiColombo mission have transformed our understanding of Mercury, but many mysteries remain. As space exploration technology advances, future missions to Mercury could provide even more detailed information about the planet's interior, surface, magnetic field and atmosphere. Seismology on Mercury. One potential future mission could involve sending a seismometer to Mercury to study its internal structure. Just as the InSight mission on Mars is using seismic data to probe the red planet's interior, a seismometer on Mercury could detect Mercury quakes, which would provide valuable data about the planet's core, mantle, and crust. By measuring seismic waves as they travel through Mercury's interior, scientists could gain a better understanding of the size and composition of the core, as well as the thickness of the mantle and crust. Seismology would be a critical tool for answering many of the unresolved questions about Mercury's internal structure, particularly the size and state of its core. A seismometer-equipped mission could detect both natural seismic activity and impacts from meteoroids, which would generate seismic waves that could be analyzed to study the planet's interior layers. By measuring how these waves move through Mercury, scientists could better understand the planet's overall density, core composition, and whether the core is fully or partially molten. A future seismic mission to Mercury could also help determine the extent of tectonic activity on the planet. While MESSENGER revealed evidence of tectonic features like lobate scarps, it remains unclear whether Mercury is still tectonically active. A seismometer could detect any ongoing seismic events, which would suggest that the planet's crust is still contracting as its core cools. Such findings would further refine models of Mercury's thermal and geological evolution. Mercury lander mission. Another ambitious future step would be sending a lander to Mercury's surface. Unlike the orbiters that have provided valuable data from above, a lander could offer in-situ analysis of Mercury's geology and surface composition. A lander could collect and analyze surface samples, conduct experiments, and provide real-time environmental data from the planet's surface. This would be particularly valuable for studying the composition of surface materials, including volcanic rocks and impact debris in much greater detail than is possible from orbit. A lander could also investigate surface temperatures and dynamics, capturing the extreme daily temperature variations firsthand. The knowledge gained from landing on Mercury could be pivotal for understanding how airless bodies in extreme thermal environments operate, and for informing future missions to similar celestial objects like the Moon or asteroids. One challenge for a Mercury lander would be surviving the planet's extreme temperatures, particularly during the day when the surface can reach over 430 degrees Celsius or 800 degrees Fahrenheit. However, recent advances in heat-resistant materials and autonomous technology could make such a mission feasible in the coming decades. Further studies of Mercury's poles. Given the intriguing discovery of water ice in Mercury's polar craters, another potential focus for future missions could be a dedicated polar exploration mission. Such a mission would aim to land in or near Mercury's polar regions to study the ice deposits directly. The lander could use drills or spectrometers to analyze the ice, determining its depth, purity, and origin. This type of mission could answer key questions about the nature and history of the water ice on Mercury. For example, it could determine whether the ice deposits are ancient remnants from comet impacts or have been delivered more recently by micrometeoroids. It could also assess whether Mercury's ice might be a source of water for future missions to the planet or other inner solar system bodies. A polar mission could also provide further data on the permanently shadowed regions of Mercury, which are some of the coldest places in the solar system despite being located on the planet closest to the Sun. Understanding the thermal properties of these regions could provide broader insights into how ice can survive on airless bodies in extreme environments. Mercury Sample Return Mission. One of the most ambitious future endeavors would be a Mercury Sample Return Mission. While returning samples from Mercury presents significant technical challenges, particularly due to its proximity to the Sun and the high energy required for both reaching and leaving its orbit, a sample return mission would offer unparalleled scientific value. Directly studying samples from Mercury's surface in laboratories on Earth would allow scientists to conduct a wide range of experiments, some of which are impossible with current spacecraft-based technology. Returning samples from Mercury could provide detailed insights into the planet's mineralogy, including the composition of its volcanic plains, crater materials, and surface crust. Scientists could also analyze trace elements and isotopic ratios that would offer clues about Mercury's formation history and the early solar system. By comparing Mercury's rocks with those from the Moon, Mars, and Earth, researchers could build a more comprehensive picture of the processes that shape the inner planets. Given the scientific challenges and costs associated with a sample return mission, this goal may still be many years away. However, as space exploration technology continues to evolve, it remains a tantalizing possibility for the future. Mercury's place in comparative planetology. Mercury holds a special place in the study of comparative planetology as it represents an extreme case within the family of terrestrial planets. By understanding Mercury's unique characteristics, scientists can draw comparisons with other planets in the solar system, such as Venus, Earth, and Mars, and better understand the range of planetary processes that can occur in different environments. Planetary density and core composition. Mercury's high density, due to its large metallic core, makes it an outlier among the terrestrial planets. Studying Mercury helps scientists understand the processes that lead to such extreme differences in core-to-mantle ratios. Comparative planetology allows researchers to explore whether similar processes could occur on other planets or exoplanets, especially those close to their parent stars. In recent years, the discovery of exoplanets in close proximity to their host stars has revealed numerous hot, rocky worlds that may share similarities with Mercury. By studying Mercury's formation and evolution, scientists can gain insights into the dynamics of these exoplanets, potentially shedding light on their internal structures and surface conditions. Magnetospheres in the solar system. Mercury is the only other terrestrial planet besides Earth that has a global magnetic field generated by a dynamo effect in its core. By studying Mercury's magnetic field, scientists can better understand how planetary dynamos work and why some planets, like Venus and Mars, have lost their magnetic fields over time. Mercury's weak and asymmetric magnetic field also provides a unique opportunity to study how magnetospheres interact with the solar wind in extreme environments. This knowledge can be applied to other planets and moons in the solar system, as well as to exoplanets that orbit close to their parent stars and are subjected to intense stellar winds. Volcanism and tectonics. Mercury's geological history, with its evidence of widespread volcanism and tectonic activity, offers insights into the range of geological processes that can occur on rocky planets. By comparing Mercury's volcanic plains and tectonic scarps with those on Earth, the Moon, and Mars, scientists can build a more complete picture of how planets evolve over time. The presence of lobate scarps on Mercury, which indicate that the planet's surface is contracting, has important implications for understanding tectonics on other airless bodies. Mercury's tectonic features suggest that internal cooling processes can lead to surface contraction on a global scale, a process that may be relevant to other planetary bodies in the solar system and beyond. Despite the wealth of data collected by Mariner 10 and Messenger and the promise of more to come from BepiColombo, many key questions about Mercury remain unresolved. Some of the most compelling mysteries include Mercury's disproportionately large core remains one of the biggest puzzles in planetary science. While the impact hypothesis offers a possible explanation, it has not been definitively proven. Other theories suggest that intense solar radiation in the early solar system could have stripped away Mercury's outer layers, leaving behind a dense, iron-rich planet. Future missions, such as those equipped with seismometers or capable of returning samples from Mercury's surface, could help scientists determine whether the planet's large core is the result of a catastrophic impact or other processes during its formation. Mercury's magnetic field. The asymmetry of Mercury's magnetic field raises important questions about the planet's interior dynamics. How is the dynamo in Mercury's core generating a magnetic field that is so unevenly distributed? Understanding the causes of this asymmetry could provide new insights into how planetary dynamos work and why some planets, like Earth, have more uniform magnetic fields. Further studies of Mercury's magnetic field, particularly by the BepiColombo mission, may reveal the processes responsible for this unusual feature and help scientists refine their models of planetary magnetism. The polar ice deposits. The discovery of water ice in Mercury's permanently shadowed craters was one of the most surprising findings of the Messenger mission. However, many questions remain about the origin, age and composition of this ice. Did the ice come from comet impacts, or was it delivered by micrometeoroids? How old is the ice, and how long has it been stable in Mercury's polar regions? Future missions that can directly sample the polar ice deposits will be essential for answering these questions and understanding the broader implications of water on Mercury and other airless bodies. The volatile elements on Mercury's surface. The presence of volatile elements like sulfur, sodium and potassium on Mercury's surface remains one of the planet's greatest mysteries. How did these elements survive the intense heat of the early sun? Were they delivered by external sources like comets and asteroids, or were they retained during the planet's formation? BepiColombo's instruments are expected to provide more detailed data on the distribution of these volatile elements, helping scientists understand how they fit into the broader picture of Mercury's formation and evolution. Mercury's broader scientific significance. Studying Mercury is not only important for understanding the planet itself, but also for gaining broader insights into the processes that shape rocky planets across the solar system and beyond. Mercury's unique characteristics, its large core, thin mantle, weak magnetic field and extreme temperature variations, offer valuable data points for testing theories of planet formation and evolution, planetary magnetic fields, and the behavior of planetary bodies in extreme environments. Mercury's distinct features provide a comparative framework for understanding how rocky planets form, evolve, and interact with their parent stars, both within our solar system and in distant exoplanetary systems. Mercury serves as a vital reference point for studying exoplanets, especially those orbiting close to their stars. In recent years, astronomers have discovered a growing number of hot exoplanets that orbit much closer to their stars than Mercury does to the Sun. These exoplanets experience intense stellar radiation and extreme temperature variations, conditions that bear resemblance to what Mercury endures. By studying Mercury's geological and atmospheric characteristics, scientists can draw parallels with these distant worlds. For example, the processes that have stripped away Mercury's atmosphere over billions of years may provide insights into how exoplanets lose their atmospheres or retain volatile elements under intense stellar radiation. Similarly, the presence of water ice in Mercury's permanently shadowed craters raises questions about whether water could exist in hidden or extreme environments on other planets. Exoplanets in close orbits to their stars are often subject to powerful stellar winds and magnetic fields. Mercury's interaction with the solar wind offers a case study for understanding how these forces shape planetary atmospheres and magnetospheres in extreme environments. The asymmetry and weakness of Mercury's magnetic field may also inform models of how magnetic fields operate on exoplanets, especially those that orbit close to their stars and are subjected to constant bombardment from stellar radiation. Mercury's heavily cratered surface preserves a record of the early solar system's violent history, including intense periods of bombardment by asteroids and comets. Studying these craters allows scientists to better understand the frequency and scale of impact events that occurred in the early solar system. Many of the craters on Mercury are ancient, dating back billions of years, providing a window into the chaotic period when the solar system was still forming. The Caloris Basin, one of the largest impact craters in the solar system, is a prominent example of Mercury's early bombardment history. This massive crater was likely formed by a colossal asteroid impact early in the planet's history, sending shockwaves across the planet and shaping much of its surrounding terrain. Understanding these impact events on Mercury helps scientists refine models of how the inner solar system, including Earth, was shaped by similar processes during its formative years. By studying the relative ages of Mercury's craters, scientists can compare the impact histories of other planets and moons in the solar system. For instance, Mercury's surface can be compared with the Moon's heavily cratered surface, as well as with the smoother terrains of Earth and Venus, which have undergone more geological resurfacing. This comparison provides critical insights into why some planets retain more evidence of ancient impacts, while others have erased much of their early history through volcanic or tectonic activity. Though Mercury's harsh environment and proximity to the Sun make it an unlikely candidate for human colonization, the planet still holds potential as a target for robotic exploration. Advances in technology could make it possible to send robotic landers or even rovers to Mercury to conduct in-depth surface exploration. These missions could focus on analyzing the planet's surface composition, its extreme temperature fluctuations, and the mysterious polar ice deposits that Messenger and future missions like BepiColombo have detected. Mercury's polar regions are particularly interesting because they represent areas where water ice has been found, in stark contrast to the rest of the planet's scorching daytime surface temperatures. While Mercury's environment presents significant challenges, particularly in terms of the thermal protection needed to survive the planet's extreme temperature swings, continued robotic exploration could yield valuable scientific data. For future exploration, Mercury's water ice deposits could serve as a resource for robotic missions, enabling long-term surface exploration without the need for resupply from Earth. While the idea of harvesting resources on Mercury may still be distant, the presence of water ice offers intriguing possibilities for missions that require water for fuel generation or life support, even if they are robotic in nature. Exploring Mercury presents significant technological challenges due to its proximity to the Sun and extreme environmental conditions. The intense solar radiation and the planet's lack of a substantial atmosphere create both thermal and operational difficulties for spacecraft. One of the most daunting challenges of exploring Mercury is managing the extreme temperature fluctuations. At its equator, temperatures can reach as high as 430 degrees Celsius during the day, while at night they can plummet to as low as minus 180 degrees Celsius. This vast temperature difference requires spacecraft to be equipped with advanced thermal protection systems. Messenger, for example, used a heat-resistant ceramic sunshield to protect its instruments from the Sun's intense radiation. Similarly, the BepiColombo mission is designed with protective thermal coatings and radiators to dissipate heat and prevent its instruments from overheating. These technological innovations are crucial for ensuring the longevity and success of missions to Mercury. Any future landers or rovers sent to Mercury would also need to be designed to withstand these extreme temperature variations. Thermal insulation, robust power systems, and the ability to operate in both the extreme heat and cold would be critical for any surface mission. These challenges, while significant, are not insurmountable, and advancements in materials science and engineering could pave the way for successful robotic exploration. Mercury's proximity to the Sun also presents gravitational challenges. The Sun's gravitational pull is much stronger near Mercury, requiring spacecraft to use more fuel and energy to reach and stay in orbit around the planet. This makes missions to Mercury more expensive and complex in terms of trajectory planning and fuel efficiency. For example, the Messenger mission used a series of gravity-assist flybys of Earth, Venus and Mercury to gradually slow down and achieve orbit around the planet. Similarly, BepiColombo is using a series of gravity assists and ion propulsion to navigate the challenging gravitational environment around Mercury. Communication with spacecraft near Mercury is also complicated by the distance from Earth and the interference from the Sun. The sun's intense radiation can disrupt signals, making it more difficult to maintain a stable communication link with spacecraft in Mercury's vicinity. As a result, missions to Mercury require sophisticated communication systems that can operate effectively in the presence of solar interference. Power generation is another challenge for missions to Mercury. Solar panels are the primary source of power for most spacecraft, but the intense solar radiation near Mercury requires special solar arrays that can withstand high temperatures without degrading. For surface missions, power systems would need to be designed to operate efficiently in both the intense sunlight of Mercury's daytime and the extreme cold of its night. Mercury, as one of the least explored planets in the solar system, still holds many secrets that have yet to be uncovered. Continued exploration of Mercury will undoubtedly lead to new discoveries that will deepen our understanding of the planet's formation, its geological history, and its role in the broader context of the solar system's evolution. As missions like BepiColombo continue to gather data, we can expect to gain even more detailed insights into the mysteries of Mercury's magnetic field, surface composition, and polar ice deposits. These discoveries will not only enhance our knowledge of Mercury itself, but also provide important context for understanding the other terrestrial planets as well as exoplanets beyond our solar system. The success of missions like BepiColombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, demonstrates the importance of international collaboration in planetary exploration. As space agencies around the world continue to work together on ambitious missions to the Moon, Mars and beyond, the study of Mercury will likely benefit from these collaborative efforts. Future missions to Mercury may involve contributions from multiple space agencies, pooling resources and expertise to tackle the unique challenges of exploring the planet. Such collaborations can also help reduce the costs and risks associated with planetary exploration, making it possible to achieve more ambitious goals. As space exploration technology continues to advance, we can expect new innovations that will make it easier to explore challenging environments like Mercury. Improved thermal protection systems, more efficient propulsion technologies, and advancements in robotic exploration will likely play a key role in future missions to Mercury. For example, the development of more efficient solar sails or ion propulsion systems could make it easier to navigate the gravitational challenges of reaching Mercury. Similarly, advancements in autonomous robotics could enable future rovers or landers to explore Mercury's surface in greater detail without the need for constant communication with Earth. As the search for exoplanets continues to expand, Mercury will remain an important reference point for understanding planets that orbit close to their parent stars. By studying the extreme conditions on Mercury, scientists can refine their models of how exoplanets form, evolve, and interact with their stars. Mercury's ability to retain volatile elements and water ice, despite its proximity to the Sun, challenges our understanding of how planets evolve in hot environments. These insights could have profound implications for the study of exoplanets that exist in similarly extreme conditions, potentially expanding the range of environments where life could exist. Mercury, the smallest and innermost planet of our solar system, is a world of paradoxes. Despite its proximity to the Sun, it harbors ice in its permanently shadowed craters. Despite being small, it has a disproportionately large iron core and a magnetic field. It presents a landscape shaped by both intense volcanic activity and tectonic forces, and its thin exosphere challenges what we know about atmospheres on airless bodies. NASA's Mariner 10 and Messenger missions, as well as the upcoming BepiColombo mission, have and will continue to unlock Mercury's secrets. Each mission has revealed more about the planet's formation, evolution, and present-day dynamics, contributing to our broader understanding of the solar system's early history and its diverse planetary bodies. However, many of Mercury's mysteries remain unsolved. How did it come to possess such a large core? Why is its magnetic field asymmetrical? And how has it managed to retain water ice at its poles despite its extreme temperatures? These are just some of the questions that future missions will seek to answer. In studying Mercury, we not only explore a planet close to home, but also improve our understanding of how planets in extreme environments form and evolve. Mercury's unique characteristics make it a crucial piece of the puzzle in planetary science, and its continued exploration will undoubtedly yield new insights that will reverberate across our understanding of the solar system and beyond. Mercury's mysteries, both known and yet to be uncovered, serve as a reminder that even in the most inhospitable regions of the solar system, there are still profound discoveries waiting to be made.